All right, in this example, we have a car that's moving with increasing velocity, and the velocity is being recorded every 2 seconds, and the data is in this table. And we're asked to estimate how far the car traveled during this time. So let's start by just graphing this velocity. All right, so there's a graph of the velocity over time. Now we're going to assume that it's probably a smooth curve. You're not going to be jumping up and down in between. It's just, well, in fact, I think it says it's moving with increasing velocity. So it's never decreasing. So it's just going to be a smooth curve. And we want to figure out a way to estimate this velocity. Now, to estimate the distance traveled, right? Now, we know that the distance is the area under the velocity curve. But in this case, it's an actual curve, right? It's not made up of horizontal line segments the way our other curves have been. But we could estimate using horizontal line segments. And that's what I'm going to show you. These are called Riemann sums. And the first Riemann sum I'm going to show you is called the left-hand sum. And it's called the left-hand sum because in each interval, we're just going to use, so we've got 2 second intervals, right? And for each interval, so our delta t equals 2, all right? And so for each interval, we're just going to use the left-hand data point, all right, to estimate the area under the curve. So we're just going to assume that this left-hand data point continues until the next interval, and then it jumps up to the next left-hand data point in the next interval. Okay, so we're going to estimate the distance traveled over the first 2 seconds just with this rectangle. Now you can see it's not a great estimate because we're missing some area here, but bear with me. This is called the left-hand sum. So we're going to start with learning the left-hand sum. The left-hand sum, we're just using the left-hand data points. And we're creating rectangles, and then we're going to find the area of each one of these rectangles and then add them all up. Okay, so this is going to be an estimate of the distance traveled, and it's one way to estimate the distance traveled. All right, so those are the rectangles that I'm going to use for my left-hand sum. All right, so let me just make, this is going to be the left hand, it's the left-hand Riemann sum, but I'm just going to call it left-hand sum. Okay, so the left-hand sum is just going to be the areas of all of those rectangles added up. So the first rectangle is 20 units high by 2 units wide, right? And then I'm going to add to that, I've got 30 units high by 2 units wide. And then I've got, the next one is 38. 38 times 2. And the next rectangle is 44 times 2. And then finally 48 times 2. Okay, so you notice that the last one, I'm really just taking these are all my left-hand data points for each interval. So I'm just taking, even though there's 6 measurements, but I only have 5 time intervals. Okay, so we say that n is equal to 5. N is the number of time intervals. All right. So now I'm noticing here that each one of these terms has a common factor of 2. So sometimes it's easier just to take the sum of all of these left-hand data points and multiply by the width of the time interval. Okay, so I'm just going to add up. It's a lot easier rather than taking 20 times 2 plus 30 times 2 plus 38 times 2 and so on. Just to add up 20 plus 30 plus 38 plus 44 plus 48 and then take the whole thing times 2. Okay, so when I do that, I get 360 feet. Okay, now you might have noticed that's not a great estimate because we're losing a bunch of area here. There's a bunch of area that we're not accounting for. And so because we have an increasing function, this is going to be our lower estimate. Lower estimate, or we could call it an underestimate. It's an underestimate of the distance that we went. Estimate. So this is an underestimate or a lower estimate. But we could do this another way by taking the right-hand data points and using those to approximate the distance, right? So I could, let me choose a different color here. If I take the right-hand data point in each interval, okay, and use those rectangles to approximate the area, which would give us the distance, right? Then we're going to get another estimate, but you can see in this case it's going to be an overestimate, right? Because you can see now these approximations are above the curve, but that's okay. It's an estimate, so we got a little error here, but that's all right. So let's take a look at the right-hand sum. We're going to call this the right-hand sum. Right-hand sum, and it's called the right-hand sum because we're using the right-hand data points. All right, so we're using the right-hand data point in each interval to approximate the area under the curve. All right, so we're going to take the first interval, we would consider it to be 30 units high times 2, and then plus, let me scroll up so I can see more of it. The next one would be 38, right? 38 units high by 2 units wide, plus 44 units high times 2 units wide, plus 48 units high times 2 units wide, and then finally 50, right? 50 units high times 2 units wide. All right, now again, I see a common factor of 2. So it's a lot easier just to, go and add up all of these. 30 plus 38 plus 44 plus 48 plus 50, and then multiply by 2. Okay, so when I do that, I got 420 feet. Okay, now that is an overestimate, right? It's too high, so I would call this my upper estimate. Upper estimate or overestimate. All right. So how can I get even better? How to be even better approximation? Well, an even better approximation would just be the average of these two. Because I know my actual curve is somewhere in between those. I know that the right-hand sum is too high and the left-hand sum is too low, just based on the curvature of this, or the fact that it's increasing. And so what I'm going to do, let me use a different pen here. I'm going to actually take the average. So I'm going to average these two. Average. I'm just going to take 360 plus 420 and divide by 2. Okay, so an even better estimate would be 390 feet. That would be a better estimate. Now you might be interested in the error here. You look at the difference between 360 and 420, right? That's 60 feet. So we could consider this to be plus or minus 30 feet, right? Half of the distance between the upper and lower estimates, 30 feet. Right? If you're interested in the error involved. Now, we're taking data every 2 seconds in this particular example. And so we could get a better estimate just by increasing the time intervals, right? If we sampled the velocity every second instead of every 2 seconds, we could get a better estimate, which is what we're going to do in example 7. So I would encourage you to try this technique in example 7. It's basically the same curve, except that now we have sampled the data every 1 second rather than every 2 seconds. And so we're going to get a better estimate. But the process is the same. We're going to come up with the right-hand sum, or the left-hand sum and the right-hand sum, and then average the two to get a better estimate. So try this one on your own, and I'll meet you in the next video to go through it.